Hi, everybody. Welcome back. We're going to pick up about where we had left off discussing the binomial distribution for a binomial distributed random variable. And we had ended class last time we had met looking at this case study regarding service contracts. And we were considering an individual who had a historical success rate of 30% on being able to convert a cold call to a sale on a service contract. So that is where this number had come from our case study. He was successful 30% of the time historically. We're going to assume again that success probability applies to any given trial, so any phone call or any cold call that this salesperson is going to make. We're going to assume the independent probability of 30% success rate, which corresponds also to a failure rate of 70%, just the complement of that probability. And we were considering an experiment where we were looking at the next 10 calls the individual would make. So we're looking at 10 possible trials in this binomial experiment. And we wanted to be able to compute the likelihoods of different sequences of successes and failures. And I think we had left off last time, but we'll reiterate on it again, about thinking of calculating the probability of making no sales out of those 10 calls. We call 10 times. What's the probability of a sequence of 10 failures in a row? Note that the only way you can get a sequence of 10 failures is with 10 failures. You got 10 slots, each of them has an F in it. That's the only combination that exists of 10 failures. So we're going to go ahead now and apply our probability function, our probability distribution function for the binomial distribution, which involved us taking some factorials. That's what these exclamation points are, rather, in the numerator and the denominator of this term. And this first term here involving the factorials, what that is doing is it's counting all the different ways that we could get X successes and N minus X failures, given that we had N trials. So in this case, we're looking for a particular sequence of 0 successes, 10 failures, okay, from the 10 trials. So we're going to just go ahead and plug in the values that we know into that probability function, and we can calculate this fairly simply here. So again, in the numerator, we're plugging in for N the number of trials. In the denominator, we have N minus X in parentheses here. Note 0 factorial is always equal to 1. So we can go ahead and plug and chug, and we wind up computing here that the probability that he does not make any calls that convert to sales out of the 10 trials here would be close to 3%. It's really 0.0282 or 2.82%. Okay, so this is how we can think about applying the binomial distribution, given that our narrative satisfies the requirements of binomial distribution, meaning the outcome of a trial, there's 2 outcomes, it's a binary outcome. That success probability is independent between trials and constant between trials. If not, then we would maybe want to think about using something like a hypergeometric distribution to model the situation. And last but not least, we have a fixed number of trials N. Okay, again, if we wanted to think about the probability of making exactly 2 sales, then we would do the same thing. Instead of X being equal to 0 now, we would use the same formula. We would plug a 2 in. And again, we can do this. Now note, there are many, many ways you can get 2 successes and 8 failures if you have 10 trials total. For example, I could get successes on the first 2 trials, failures on the last 8. I could get successes on the last 2 trials, failures on the first 8. And there's many different combinations of 2 successes and 8 failures in between that we could consider. Now, again, when doing this calculation here, this first term, okay, with the factorials, that is telling us how many different ways, how many different combinations we can generate where we're looking at combinations of exactly 2 successes and 8 failures. Okay, and that number over here comes out to 45. Okay, that is the number of different ways we can get 2 successes and 8 failures in 10 trials. Okay, so again, we can plug and chug here, and we see the likelihood that he converts exactly 2 calls, given his historic success probability out of the 10 calls here, would be 0.2335 or around 23.35%. Now, this is all well and good, but you can imagine if I wanted to know what's the likelihood that he makes 2 or 3 successful calls. Okay, then I have to do this calculation 2 times because I'm taking the union and I have to add the likelihoods of those mutually exclusive events, getting 2 calls that are successes on one day or getting 3 calls that are successes on one day. So what we're going to do in a moment is we're going to invoke the use of a probability table, okay, that corresponds to the binomial distribution. So these statisticians have actually cranked out table values for us to calculate these probabilities for given parameters like x, n, and p. And we're going to exploit the structure of these tables to actually save us from having to do 2 things. 1, a ton of computations, adding up probabilities when we take unions of event in the binomial framework. And 2, we're going to avoid using calculus later on when we look at different types of continuous probability distribution, specifically the normal distribution, which we're going to discuss fairly extensively in the next segment. So back to the service contract. Okay, we already calculated the probability of making 0 sales exactly, but I want to make sure we can do this using the binomial distribution table. So you should be able to find this table that's been posted in the online course page where the other tables are posted as well. So make sure you can go find that table. It looks generally like this. The one that I posted for you guys is many, many pages. So what I've pulled here is specifically the table, or rather the part of the table that corresponds to 10 trials. Okay, so you're going to want to go and find the part of the table that corresponds to exactly 10 trials. And then all we're going to do here is we are going to use our knowledge of the parameters we've been given. We have a 30% success probability, and that is what is measured along the horizontal axis along that top row there. Okay, so the success probability tells us which column to look at on this table. So we're using a 30% success probability, so we're going to pick the 6th column here, which corresponds to that success probability, and then we're going to go ahead and we're going to find the row in the table that corresponds to exactly 0 successes. And note that if we do that, we get a table value here that matches up exactly with what we had calculated on that previous slide. So go ahead and make sure you can check that that answer matches up with what we had seen already. Now, the one thing I do want to be clear about are these table values. They're not exactly the probability that x equals 0. In fact, you'll notice I've kind of written this carefully at the bottom of the slide. This is actually the probability that our random variable is less than or equal to the value we're looking at in this column. So if we were to go over, for example, to the row where it's x is equal to 2 successes, we would see this probability of 0.3828. That's actually the probability of 2 successes or fewer. Okay, so that actually includes the 2 probabilities above, in addition to the event that we are looking at here specifically, which is 2 successes or fewer. Okay, so this binomial table, it is giving us cumulative probabilities. If I want the probability that x is exactly equal to a particular value, what I'm going to need to do is to find that particular value, x, and then I'm going to look at the row of the table directly above it, x minus 1, and I would subtract those 2 probabilities. And we're going to go through a few examples in a moment if you didn't catch that 100% with this notation. Similarly, if I wanted a probability that the random variable big X is greater than or equal to some threshold value, then we can use the structure of the table again and recognize that 1 minus the probability, again in the row directly above little x, okay, would be the complementary probability and give us the event, or the likelihood of the event, that the random variable x was greater than or equal to the value lowercase x that we are comparing against. So let's go ahead and make sure we can see this. We already computed the probability of making exactly 2 sales using the formula, but we want to make sure that we're comfortable using the table as well. So let's go ahead and use the table to do that. So here is our table. And again, the table shows cumulative probabilities. Note that I'm looking at the table here for n equals exactly 10 trials. We're still using the same success probability of 0.3. But now, if we're looking at the probability that they make exactly 2 sales, I'm going to need not one, but I'm going to need 2 rows of this table. I'm going to need the row corresponding to 2 or fewer successes, which includes 1 and 0. And I'm going to need the row that includes 1 or fewer successes. And what we're going to do here is we're going to take the bottom value, 0.3828, which is the probability of 2 or fewer successes, which includes 2, 1, and 0. And we're going to subtract out the probability of 1 or fewer successes, which includes just 1 or 0. And what we will be left with in that instance here when we do this, when we subtract those 2 values in the green box, is we would get the probability of exactly 2 sales, of precisely 2 sales, which matches with our result from utilizing the actual formula for the probability distribution function for the binomial distribution, which came out to, again, 23.35%. So we want to get comfortable using this table to help us expedite some calculations in situations where it might warrant it. So let's go ahead and look at another example here. In this example, it's important at quick oil change shops to ensure that a car's service time is not considered to be late by customers. Let capital X be the number of cars that are late out of the total number of cars serviced. So capital X is our random variable here, the number of late cars. Let's suppose historical data suggests that the likelihood of a car being late is around 10%. So we could look back at all of our data and we see that out of the past 100 days, or the past 100 cars rather, about 10 cars were late. So we get this estimate, and we're going to assume that success estimate here, or rather the failure probability, depending on how you want to think about these events, you might define the event of the car being late a success or a failure. Here, we're actually going to define the car being late as a success, even though it's a little counterintuitive. That's the event of interest. Okay, so our success probability here is 0.1. And we're going to, again, think about what is the likelihood that exactly 2 of the next 10 cars serviced are late. Okay, so you'll note if n is equal to 10, okay, we have 10 possible trials. So I'm still going to grab that part of the table where we have 10 trials. Okay, and you'll notice the success probability is a little different from the last example. And we want to figure this out. So we know the following. We have 10 trials. Success probability is 0.1 of us administering a late car, and 90% failure probability here. And we want to know what is the likelihood of exactly 2 cars out of the next 10 being serviced late. So next thing we're going to do now is we're going to go to our binomial distribution table. I'm going to look up that success probability of 0.1. And again, if they want the likelihood of exactly 2 cars, then again, we're going to need 2 rows from this table. I'm going to need the row that corresponds to 2 or fewer, which is the row with x equals 2. And then we're going to also look at the row that corresponds to 1 or fewer late cars, which is the row corresponding to x equals 1. And as we saw in the last example, I'm going to have to subtract those 2 probabilities from each other. If I take the probability of 2 or fewer minus the probability of 1 or fewer, that gives me the probability of exactly 2 cars being serviced late, which comes out to 0.1937 or 19.37%, which is choice D. Okay, so if you were given the parameters of the probability distribution for this binomial random variable, if you know the number of trials and you know the success probability, one thing you can calculate right off the bat is the underlying mean of this random process here. So if I wanted the population mean mu, I take the number of trials n times the success probability p. Okay, let's try it. Let's suppose you had a 100-question exam and you were randomly guessing, okay, on every single question, every one of those 100 questions. And suppose each question had 4 answer choices, meaning on one question, your success probability would be 25%. Okay, if we wanted to know on average, how many questions would you get right if you answered all 100 of them this way? Okay, then the way we can calculate that is by taking n, the total number of questions, the total number of trials, and we can multiply it by p, the probability of success on a given trial. So if I had 100 questions times a 25% chance of success, that would tell me I would be getting 25 questions right. Similarly, we can also compute the standard deviation. Okay, so if you've been reading in your book, which is always a good thing to do, you should be doing that. You'll notice the book also talks about the parameter P bar quite a bit, the population proportion in terms of categorical data. And these are very closely related to some of the measures that you will see in your textbook. So again, N is our sample size, the number of trials, P is the success probability, and 1 minus P then is the complementary failure success. Now, the next slide I'm going to show you, the point of this slide is to understand that there are many different ways of describing a particular event in terms of verbal narrative. If we wanted to think about which of the following sketches has correctly highlighted in yellow the event fewer than 2 successes. Okay, fewer than 2 means we're not going to include 2, but we will include 0, we will include 1. That looks a lot like choice A. Okay, you'll note that choice B is a little bit different. Choice B is not fewer than 2 successes. It's really the complement of that event, 2 or more successes, assuming that the numbers go past 4 to the right off the screen here. Okay, so we could say this event 2 or more successes several different ways. We could say 2 or more successes. We could say at least 2 successes. Okay, and similarly, the bottom event is a little bit different as well. Okay, we could think of that as not 2 successes, okay, which would include 0, 1, 3, 4, etc. Or we can think of that as fewer than 2 or more than 2. We could think about using the union between the fewer than 2 event and the more than 2 event. Okay, so you have to read the problem narrative very carefully to understand exactly which probability you're being asked for here. So let's go ahead. We're going to take a look at another case study to wrap this up. Then we'll look at some simulations of different discrete distributions for the binomial random variable for different parameters. And we'll see that it's very closely related to something called the normal distribution, which is a continuous distribution, which we're going to talk about extensively in the next segment. So this is a pretty funny case study here. It's a pretty old case study, but the Wall Street Journal reported that to the chagrin of Microsoft management, it turns out about 10% of Microsoft employees tend to carry iPhones. They're iPhone users. And of course, this is somewhat ironic given that Apple and Microsoft are competitors. So this is related to some peril of being an iPhone user at Microsoft last September. Specifically in an all-company meeting in Seattle Sports Stadium, one hapless employee, one poor guy, pulled out his iPhone to take a photo of himself with then CEO Steve Ballmer. And Ballmer snatched the iPhone out of the employee's hand, threw it on the ground, and pretended to stomp on it. I was joking, but it was, he was trying to get a point across that you shouldn't be using the competitor's products. And the first question we're going to ask here is, if we were to sample 20 Microsoft employees, you randomly select 20 Microsoft employees. So we're going to think about 20 trials. Question is, given this quote unquote success probability of 10%, okay, based off of this historical average, question is, given that we sampled 20 workers, if there's a 10% chance one of them independently would carry an iPhone, then on average, what is the expected number of Microsoft employees with an iPhone from this group of 20? Well, all we have to do then, given this information, is apply our expected value formula for the mean, okay, for the population mean here of this random process. So we would take 20, we would multiply it by 10%, and we'd be able to see that on average, we wind up getting a mean of exactly 2 employees out of those 20 that would be iPhone users, that would have an iPhone. Okay, similarly, if we wanted to know the standard deviation for the number of Microsoft employees with iPhones, we know on average there'll be 2 of them out of the 20 that are randomly selected. But what is the standard deviation? Well, again, we can more or less plug and chug here given the formula for the standard deviation in the slide here. So let's go ahead and do that. If we plug in 20 for N, our success rate, 10% for P, and then 90% for 1 minus P, the failure rate, and take the square root of those products here, we wind up getting our value of sigma, the standard deviation for the random variable that is the number of employees with iPhones at Microsoft out of these 20. And we see on average out of these 20 about 1.34, okay, are above the mean of 2 or below the mean of 2. So this is how you would compute the standard deviation given these parameters of a random variable that has a binomial distribution governing its process. We can go ahead now and again think about invoking our use of the binomial table as we had done before. In this question, we're going to ask, what is the probability that no more than 6 employees are iPhone users? Okay, now no more than 6, we have to be careful about that. Okay, that could be 0, could be 1, 2, 3, 4, 5. Does it include 6? I think so. No more than 6 could include 6. Okay, so we're looking now for the following. What is the probability that the random variable x falls in any of these events here, 6 or fewer? Now remember, the binomial table gives us cumulative probability. So if I found the row that corresponded to exactly 6 successes out of these 20 trials, okay, that includes 6 or fewer. So I actually only need to find one particular table value here. And let me take a moment and switch my screen so you can see exactly what that looks like. Okay, so note I have the binomial table pulled up here for the situation that we're looking at. And you'll notice the table is very, very big. There's like 8 pages of it. So I'm specifically looking at the one that corresponds to exactly 20 trials here. Okay. And we had a success probability of exactly 0.1, that's up top. So I'm now going to go down to the row that corresponds to 6 successes or fewer. So I'm going to go down that success probability column to 6 or fewer, given that we had 20 trials, and I can see here that comes out to 0.9976. Okay? And that is going to be the correct answer to this particular problem that we've been looking at. All right, so let's jump back to the slides here, and we'll go ahead and answer that question and move on to the next. Okay, so back on the slide here, we found that probability 0.9976, so we are in good shape, in some good shape, which is choice D. Okay, next question we're going to look at. Okay, still same case study, but now the question changes the narrative just a little bit. So recall up here we were looking at the event more than 6, or sorry, no more than 6, which was 0 through 6 inclusive. But now we're going to change the wording just a little bit, and we're going to consider now a situation where we're asking essentially the same question, but we want to know what is the probability that less than 6 employees are iPhone users. So less than 6, okay, that has now removed one event of interest, right? Last problem, we were looking at 0, 1, 2, 3, 4, 5, or 6 or fewer. But if we're considering the probability that big X is strictly less than 6, then that only includes 0, 1, 2, 3, 4, or 5. Okay, which means now when I use my probability distribution table, I need to go down to just one row, but I need the row for 5 or fewer. Okay, so take a moment, go check that on your own. And you can pause the video if you need to, and then I will reveal the answer. So hopefully you had found using that table that the probability of 5 or fewer successes given 20 trials and a 10% success rate comes out to 0.9887. Moving along. The next question asks, what is the probability that exactly 6 employees are iPhone users? Now remember, exactly 6 meant we had to go get 2 table values. I need the row corresponding to 6. I need that table value. But I also need the table value corresponding to 5. So again, if we jump to our table here, we should be able to see that. So again, we're back at the table. We want to figure out what is the probability of exactly 6 successes here. So we're going to go down to that row using our, again, the 20 trial portion of the table here. We're still using that 10% success probability. So I'm going to go down here. We're going to find that 0.9976 value, which corresponds to exactly 6 successes or fewer. And we're going to have to subtract from it the value coming from the row that corresponds to 5 successes or fewer, which is 0.9887. Okay, so we should get a pretty small number when we subtract those things. And let's go ahead and make sure that that is indeed the case. We're going to subtract those two values. And we can see here now that we were essentially correct. It was a really low probability. We took the difference between the table value corresponding to 6 or fewer successes minus the table value corresponding to 5 or fewer successes, and we wound up with a probability of 0.0089 is the difference between those two table values. All right, moving along. So next problem. A question is asking us here, again, similar, but what is the probability that at least 6 employees are iPhone users? Okay, now we saw before there are a lot of different ways to think about this event, at least 6. Okay, another way to think about that is it's 6 or more, and there's 20 total that are possible. So we could go to the 20 row, and we could subtract out the row 5 or fewer. That would be one way to do this. Or we could recognize that we have some knowledge of complementary probabilities at our disposal here. And we could recognize that the event 6 or more is the complement of the event 5 or fewer. So if I went back to the table and I found that row, I found the table value corresponding to 5 or fewer successes, which we actually saw on the last example, which we needed that table value to use. We could take 1 minus that table value, and we would be able to calculate that the probability of 6 or more successes, from 6 to 20 folks with iPhones at Microsoft, given that we sampled 20 employees, that will be around 1% or 1.13%, as we see here. Now, before we wrap up, I want to talk just a little bit about the shape of a binomial distribution. The shape of the binomial distribution depends critically on 2 values. The first is the success rate, P, and the second is the sample size, or the number of trials, N. Okay, in general, the binomial distribution is going to be positively skewed if the success rate is lower than 50%, and it will be negatively skewed if the success rate is greater than 50%. Okay, if the success rate on any given trial is a coin toss is equal to 50%, okay, then you wind up with a symmetric looking discrete probability distribution for the binomial random variable. Even in cases where P is not equal to 50. Okay, so if we're dealing with either the positively skewed case or the negatively skewed case, okay, in those situations, the degree of skewness turns out to go down as the number of trials or as the size of the sample space increases. All right, so here are a few different pictures. Okay, and I want you to just look at each column and move down. So here in the first situation, we have a probability for the binomial process that is smaller than 50%. And you'll notice we're getting some positive skewness here, right? That tail's getting pulled to the right even farther. But as the number of trials goes up, okay, the shape of that binomial distribution looks more and more symmetric. Okay, if P is exactly equal to 0.5, then it's symmetric no matter what we do, but as N gets bigger, it looks even more and more and more like a nicer bell-shaped distribution. And when P is 0.8, we get some negative skewness for low values of the number of trials N, but as we increase those, right, to 10, to 20, the resulting distribution looks less skewed and looks more symmetric. So that is it for our discussion of the binomial distribution. Make sure you're reading up on both the Poisson and the hypergeometric distributions. They apply in other situations where the binomial does not, with respect to discrete probability distributions. And in the next segment, we're going to pick up talking about a very important distribution, a continuous distribution known as the normal distribution. And the normal distribution is the most important distribution to study. I wouldn't say just in this course, but probably in general in statistics, in that it turns out to describe a lot of naturally occurring data in terms of when we're computing sample means. So we're going to see a result later on called the central limit theorem that suggests that most data that we're going to deal with will have sample means that are normally distributed, provided we have enough of that data. So hope you enjoyed that discussion of binomial distribution and how to use the table to calculate probabilities instead of just cranking or grinding through with the probability formula here. And I will see you in the next segment.